Hi kids, time to do some linearization and differentials. This is one section in the book, but it really is two objectives, right? So number one, we're going to find the linearization, which just is a fancy way of saying write the equation of a tangent line, which you've been doing since Unit 3A. And of course, this is an application of derivatives because to write the equation of the tangent line, you need the derivative. This linearization of curves is tied to something called differentials. And differentials is a way to estimate using the derivative in the tangent line the change in your original function, because that is approximated by the change in your tangent line, the linearization function. And change is represented by small d, delta, and your original function is y. So differential of the original function y is going to be approximated by the actual change, and I'm just going to differentiate I'm going to use triangle for delta this time. Okay? I know that sounds confusing, but I'm going to try to unscramble that. But let's do old news first. So in the warm-up that we'll do in our live session, the function I gave you was the square root of 1 plus x, and I asked you to find the equation of the tangent line. You found the equation of the tangent line by taking the derivative and then plugging in 0 to the derivative. Then you created the equation of the tangent line. You got this value by plugging in 1 to the original. I'm sorry, 0 into the original. You got the square root of 1, which is 1. And then you moved, that's just 1/2 x, and you added plus 1. And then I told you to use some new notation on your tangent line. Instead of calling it y, call it the linearization in terms of x. Of the function, this is the linearization of the original function, which just means at x equals 0, there's a little cloud around here. If you look in that little cloud, the tangent line approximates the curve. They are exactly the same at the point of tangency, but you can see that the curve, because the square root function is concave down, that the actual values of the function are smaller than the values of the tangent line, or equal to, but only at the point of tangency, right? At the point of tangency, f of x is equal to its tangent line, and the point of tangency, of course, was 0. All right, so that's what we talked about in the warm-up. So look at this chart. Compare just what I was visually talking about. This is the point of tangency. Here's your original values. Here's your approximation values from your tangent line. And here's the error in using your tangent line. So of course, one wouldn't really use linearization on simple functions, but you would on harder functions. And this is, at points, this is pretty easy to program. So of course, the original function at 0 is 1. The tangent line at 0 is 1. So the error in using your tangent line to approximate, your error is 0. But at 0.5, right? And just use your calculator to do this, right? I don't expect you to do this by hand. If you plug in 0.5 to the function, you are going to get a value that is lower than the tangent line at 0.5. Can you see that? At 0.05, the function value is under the tangent line. So that distance, that vertical distance between the red and the blue dots, that's your error in using the tangent line isn't exactly the function, but it's a small error, right? Can you see is that you move away from the point of tangency, right? I'm moving away, I'm increasing delta x, right? And when I plug in 2, I get the square root of 3. But when I plug in 2 to here, I get 1/2 of 2 is 1. 1 plus 1 is 2. Right? This is approximate. This value is still lower. What is that, 1.7-ish, I think? Is lower than the tangent line because, again, here at 2, oops, the tangent line is blue, the function value is red. So you can kind of see that that error there is larger, right? So as delta x increases, your error increases, right? And I really just care about the absolute value of this, right? I just want to know what my error is. So this is like 0.7-ish, right? A much larger error than what I had up here, and that's the whole idea, as long as you stay close to the point of tangency in the domain, the range values of the linearization function, the tangent line, will be very, very close to the original function. And as you move away from the point of tangency, you can see the curve, right, diverges away from the tangent line. So that is the concept of using a linearization to approximate a curve, right? Linearization is the tangent line used to approximate. Because after all, even computers, processors, right? They're faster computing values with lines than they are with more complicated functions. So here are some important linearizations near 0. Right? This is from the warm-up, and it turns out that any function, right, if f of x is equal to any function of the type 1 plus x to an exponent here, the linearization function will always be 1 plus that exponent times x. So for example, if you had f of x is equal to 1 plus x to the 2/3, instead of plugging values into that, as long as you stay near 0, you could use instead its tangent line, and without doing the derivative and the chain rule and all that, there's linearization at 0. Crazy, right? And then look at the next ones. They're kind of cool. Here's sine x. Doesn't it look like its tangent line at 0 is y equals x? Do you know how many communications, your cell phone, the satellites, the rockets, all that kind of stuff deals with sinusoidal curves? And the approximation of sine x is just y equals x, right? This is the linearization. As long as you stay near 0, you can approximate sine with just y equals x. That's crazy. Cosine, you can approximate as long as you stay near 0. Whoops, sorry. Right? The tangent line here is y equals 1. So as long as you stay close to 0, instead of plugging something into cosine, you can just plug it, you can just say, man, it's approximately 1. It's pretty powerful. Tangent. Again, can you buy the fact that the linearization around 0 is y equals x? So as long as you stay around 0, plugging in values to the right and left of 0 into tangent, you can just say, it's the same as the x. Close enough. Crazy. So again, this is a super important idea that for any value of the domain, the tangent line is a very good close approximation. The tangent line, which we are calling now L of x, the linearization of the function f, as long as you stay close. Close around the domain, cloud around the domain, cloud around the function. And further, I can also tell you, if I know the concavity of the original, I can tell you then as if the original was concave down, the tangent line approximations will either be greater than the function or equal to at the point of tangency. Conversely, if you had a function that was concave up and you drew a tangent line at some other x equals a, right? You pick some other domain value here. You stayed in a cloud here, and you drew a tangent line, a terrible one, as you can see. Hopefully there you can see that, sure, at the tangent line, the red curve is the same as the blue line. But in this case, your linearization values, your tangent line values, are always below or equal to at the point of tangency, the function. And as you get further away from the point of tangency, your error increases. So that's why you want to stay in your little cloud. And we just have a new name for the tangent line. We call it the linearization because if you zoom in on the cloud, the curve looks like its tangent line, the linearization of the function. So now I want to show you some, like, people and math books love to talk in this fancy language, but I want to translate this for you, right? What is the linearization of an original function at a domain value? So let's pretend that the domain value is 2. So they give me x is equal to 2, which means y is equal to plug in 2. And that means the derivative, right, or the slope of my linearization is the derivative at 2. So for example, what if I gave you 3x cubed? What if I said the original was y equals 3x? Oh, why don't I just say x cubed? X cubed. So y of 2, so x is equal to 2, y of 2 would be 8, right? 2 cubed. Y prime is 3x squared. So y prime, or f prime, at 2 would be 2 squared is 4, times 3 is 12. The equation of the tangent line then would be y minus 8 is equal to the slope times x minus 2. And then if I want to make that in the linearization form, I replace y With L of x, I take the 8 and I move it over to the other side. So you see this minus f of a is now on the other side of the equal sign, but it's positive. And then this did not change. And then I replaced y with L of x, right? Y becomes L of x. F of a was my 8, right? Because for us, a was 2, plus the derivative at 2 was 12. That's how I write my linearization. And all this language in that box, the formula is just the point slope form of the tangent line with, right, this value, your y value, added to the other side. And of course, it doesn't matter if you put the 8 here or you put the 8 over here. It doesn't matter. Addition's commutative. This is just how the formula will appear in books or on websites. The standard linear approximation, which is just the equation of the tangent line, to a function f at a domain value. That's all that is. Point slope form of a line. As long as you stay close, as long as you choose x's close to the x coordinate of tangency, then the original range is really, really close to the range of the tangent. This is just using your tangent line to approximate an original function. Because we are using a tangent line, which is a degree 1, we can also call this a first order approximation, which, foreshadowing, does mean we're going to learn about second, third, and fourth order approximations as well, but that's not till second semester. So let's look at this. In this fancy language, find the linearization L of x of f of x at x equals a. How accurate is this approximation? L of a plus blah, 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 blah. Oh my Lanta, right? Find the linearization. Write the equation of a tangent line. To this function at -4. Then, how accurate? Calculate the error. That's what it means. So, step 1. Please don't forget the chain rule. Bye-bye. So what do I have here? -4 squared is 16. 16 plus 9 is usually 25. So f of -4 is equal to 5. No, that is not plus or minus. That's when you're solving a quadratic, not simplifying a radical. And f prime of -4 is -4 over square root of 25, which is 5. So 3, my linearization at -4 is equal to 5 plus the slope times x minus. And again, I don't care about the order. I don't even care if you call it L of x. You can still call it, you can just call it y if you want. -4, which of course makes that a plus. -4/5 is my slope here, and 5 goes there. If they asked you for the error, which they did, what they want to know is, how good do you think L of x does approximating f of -4? Well, hopefully you can see, right? It's going to be off kind of by this much, right? What your change is. So what is f of -4? We already know. That's 5. What's L of -4? Well, I'm going to plug -4 into there. Whoops, sorry. I don't want to approximate -4, silly. That's going to give me 0, dippy. Not -4. That's what this part means. I want to take -4 and change it by 0.1, which is a small change. If you change the original by 0.1, how much does that x by a small amount? What's the change in y? So I want to take f of -4 plus 0.01. And yes, you'd have a calculator to do that, right? I don't expect you to take -3 point whatever, 0999, whatever that is, and square it and add 9. No, I expect you to use your calculator. But you will see that these values, since you have a small change in your x, your error is going to be very small. As opposed to if I had made this delta x, right? If I had changed the x, -4, what if I'd said, oh, approximate, x equals -10? No, you would not use your tangent line then. You would make a new one, right? So the big idea here is, given an x value of -4, as long as you stay within that little cloud, right, reasonably close, and I mean very close, the tangent line, right, which we said had a slope of what, -4/5, you can use the tangent line to plug in values near -4, and you will get range values very, very close to the original function. Okay. All right, let's go on to differentials. Differentials does represent the small change in y, or the small change in answers, range. But it is an approximate. Now, for those of you that have taken AB and already done related rates, what I'm going to say next is going to make a little bit more sense. Please do not confuse differentials with related rates. Okay, there is a big difference, and the big difference is differentials only approximates change, and there is no time involved in the problem. When we get to related rate problems, we are going to find the exact change at specific times. So here's some background conceptual information, right? Do you remember when we first did the definition of derivatives, and we talked about how if we take the slopes of the secants, right? Slopes of the secants, where you have the change in y over the change in x. As you applied the limit, and the limit as delta x approached 0, you are getting the slope of the tangent, and we used the d to mean that the delta y, the change, has gotten very, 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 very small. So here's that same picture that I had before. A tangent line drawn at a point of tangency, a comma f of a. Now, I added a little bit to x. 0.01, 0.1, 0.5. 0.5 is actually a little bit large. And I'm, of course, going to make my delta x large here because I want to accentuate the drawing. But there is my change in x. But notice, so pretend again that this is 2. And this is 2 plus 0.5. So if I plug 2 into the function, I get my y height, my answer. If I plug 2.5 into my function, I get the height on the curve of when x was 2.5. Notice the vertical change here. That is the actual change in y values when you changed x from 2 to 2.5, right? This vertical change. But now look at my tangent line. What happens when I plug 2.5 not into the original, but I plugged it into the tangent line? Can you see that the tangent line value lies a little bit above the curve? But this height right here, is the height of plugging 2.5, 2 plus delta x of 0.5, into the tangent line. This vertical distance is the change in the tangent line, because remember, the tangent line and the function are equal here. Right? Do you see that? That is the actual change. But notice the error in using the tangent line, as we said previously, the error in using the tangent line is just right there. So, as we shrink delta x to dx, dy, the actual change in y, becomes smaller and smaller. Yes? Delta y becomes dy as delta x shrinks to little dx. So look at what I've said here. That little dy, as we shrunk delta x, remember we had triangle y, delta y, which was that vertical distance, as we shrink delta x, triangle y becomes dy, the differential of y. The differential in the original is approximated by the differential in the tangent line. So that is the tangent line at 2 plus, not 0.5 anymore, but like 0.0005, minus the tangent line at the point of tangency. But what is that? Can you see what that is? Just doing some algebra here. I replaced L of this x, which is 2 plus 0.0005, with the tangent line formula. Do you see that? Those two red boxes are the same thing. That's the formula that you wrote down 2 slides ago. And then look what happened here. What the heck? Why did I magically replace the tangent line at the point of tangency with the function at the point of tangency? Because those two are equal, right? When you plug the tangent line into the x-coordinate of the point of tangency into the tangent line, or you plug the x-coordinate of the point of tangency into the function, they are the same, right? The tangent line and the curve are the same at 2, comma, f of 2. or whatever A you want. But now look at what's happening here, right? Math is cool. Look at this. F of A cancels with negative F of A. A cancels with negative A. And the differential in the original function is simply the slope times dx. Now, check this out. Remember, slope is really dy over dx, right? Slope is dy over dx. What happens when you multiply dy over dx times dx? By, and you get dy. OMG. Rise over run times run is just rise. All right, well, that's swell. Copy this formula down. You don't ever, if you don't understand that or that blew your mind or you're like, that's not cool, Ms. Getz, that's okay. Just write down this formula. You do need this formula. As long as you are talking about a small change in x, that's what dx represents, a small, it's not triangle x, it's delta x, which means small change in x. If you change x by a little bit and you want to know if using what's the small change in y, the small change in y can be found by multiplying times the derivative. Let's use this. All right, I have a circle of radius 10. If you increase the radius, right? The radius, no matter where you go, is 10. If you increase the radius, how much will the area change? Well, wait a second. Let's back up for a second. What is the area of this circle? Right? Area is pi r squared, right? So the area of this circle is 100 pi. So suppose you're making, right? You're manufacturing, I don't know, did they give me units? No, of course not. Let's pretend this is, what, centimeters maybe? Have you seen a bunch of those stickers now that they have to make and put on the floor for 6 feet, like, oh, stand here, and then a sticker somewhere else for stand here, right? To keep, to help people keep a distance of 6 feet, right? For social distancing. What if you're manufacturing those, but your machine isn't exact all the time, and you're supposed to make a bunch of circles with an area of 100 pi? Right? Which means you need a radius of 10. What if you're off a little bit? So what if instead your machine made a circle whose radius was 10.1? What is your new area? Or what is the change in area, I should say? Now, obviously, this is a simple equation. I can just simply compute and then subtract. But the idea here is to show how differentials could do this for you. So the first thing I'm going to do is take the derivative of the area. Notice what I'm with respect to, right? I don't have an x in there. If you want to make this pi x squared, fine. But this variable is r, so I'm taking the derivative of the area with respect to the variable I see. I brought down the 2 pi r to the first, and there is no chain rule here. So there's the derivative, a prime. The differential of the area then, and you know what you can think of? Think of multiplying both sides by dr here, right? Get dA by itself. The differential in the area is 2 pi times your original radius times the small change. So 2 pi times my original radius times the change in the radius. So the change in the area is going to be 6.28-ish. That's right, square units. That's not that small, right? And I only increased the radius by 0.1. You might want to know that when you're manufacturing these stickers, right? Or whatever it is you're making. And you can already know, so you're like, so what you say to your machinist or whoever's making this, you're like, look, you need to make the cuts of the radius. You need to make sure the radius is under, right? That you're not off by 0.1 centimeters, inches, whatever this is in, right? You need to keep it under because I can't deal with a change in the area of 2 pi units. All right. So that's the end of linearization and differentials.